Have you ever stopped to wonder what gives a pine forest that sharp, clean smell? Or what gives an orange its zesty punch? Well, today we're going to dive into the secret chemical language of the natural world. We're on a mission to uncover the one simple building block behind nature's most iconic scents and vibrant colors. It's pretty amazing.
All right, let's jump right in. And we're going to start by connecting some dots that you probably never even thought to connect before. We're constantly surrounded by these incredible sensory experiences, but they all, and I mean all of them, share a hidden connection.
So really think about it for a second. A pine tree, an orange, and peppermint. On a surface, they seem completely unrelated, right? One is sharp and woody, another is bright and citrusy, and then you've got that cool minty blast. So what on earth could possibly be the common thread here?
Well, here's the thing. The answer isn't what they smell like, but how they're made. It turns out nature is this incredibly efficient architect. It uses the exact same fundamental ingredient to build this just staggering variety of molecules. So I think it's about time we pull back the curtain and solve this little mystery. Let's meet the molecule that makes all of this happen. The answer is terpenes. And listen, this isn't just one molecule we're talking about. It's a massive, and I mean massive family of over 20,000 different compounds. They're the primary thing you find in the essential oils of plants and flowers, and they're pretty much responsible for all those distinctive aromas. And here's the real secret sauce, the magic behind it all. Every single one of those 20,000 plus terpenes is built from this one simple thing, the isoprene unit. It's just a basic 5-carbon structure. Honestly, the best way to think about it is as nature's universal Lego block. Okay, so how does nature take this one simple Lego block and build such a breathtaking variety of molecules from it? Well, it all happens on this highly efficient biological assembly line. And it's this beautifully simple 3-step process. The plant starts with some basic raw materials, right? It runs them through this complex little biological factory, and what comes out on the other end are these energized, activated isoprene blocks, just ready to be snapped together. And here's the really elegant part. Nature has a very simple rule of construction. It takes these activated Lego blocks and just links them together, usually in a super straightforward head-to-tail fashion, to form chains. That's it. Simplicity is what creates all the complexity here. And this is where it gets really, really elegant. The type of terpene that gets created is decided simply by how many of those isoprene blocks get linked together in the chain. It's basically a classification system based on simple math. Just take a look. If you snap 2 units together, you get what we call monoterpenes. 3 units, sesquiterpenes. 4 gets you diterpenes. You get the idea. It's this incredibly logical and organized system, and it's all based on just simple addition. Okay, so let's start with the smallest and maybe the most common group, the ones built from just 2 of those Lego blocks. So 2 isoprene units, that creates the monoterpenes. Now, these guys tend to be really light, kind of volatile molecules. That just means they evaporate super easily and travel right to our noses. And that's exactly why they're responsible for so many of the smells we recognize, like the menthol from peppermint oil. Okay, so that's the small end of the scale. Now let's jump all the way to the other end. What happens when nature assembles a much longer chain, using 8 of these isoprene blocks? Well, that creates what we call the tetraterpenes. Now, with this many blocks, the molecules become much larger and heavier, and their size is absolutely key. They're way too heavy to just float up to our noses as scents, but their long, complex structures are perfect for something else, interacting with light. And that is why they become the pigments that create such vivid colors in nature. Okay, so now let's see how this simple building process creates some truly amazing and essential molecular masterpieces. We're going way beyond just pleasant smells and pretty colors now. So, meet squalene. This is a triterpene built from 6 of those isoprene units. And what's so fascinating about this one is that it's not just in plants. Your own body produces it. It's an absolutely vital starting point for making things like cholesterol and vitamin D. And this is a brilliant example of a tetraterpene. It's called lycopene. And that long chain with its 11 double bonds, that specific chemical structure is what's perfectly tuned to absorb light and reflect back that brilliant red color that you see in a tomato. It's amazing. And it is the exact same story for beta-carotene. It's another tetraterpene, just a slightly different structure. And that tiny difference changes how it interacts with light, resulting in that signature orange color you see in carrots and apricots.
Okay, so the really crucial point here is that these molecules do so much more than just smell nice or look pretty. Their unique structures give them powerful biological properties, properties that we're really only just beginning to fully understand and use. Because they're so biologically active, terpenes have become incredibly important. I mean, in the food industry, they're used as natural preservatives, and in medicine, they are a huge, huge area of research for developing all sorts of new therapies.
And this is why things get really exciting. Research is showing that different terpenes have powerful, well, anti-cancer, antimicrobial, anti-inflammatory, antioxidant, and even anti-allergic properties. This is basically a treasure trove of natural chemistry with absolutely massive potential for human health.
So the next time you smell a pine forest or peel an orange, remember the humble terpene, that simple little Lego block. It really makes you wonder, doesn't it? What other secrets are hiding in the scents and colors all around us, just waiting to be discovered?